We want to apply the abstract theory to the problem of quadrature. To illustrate the ideas, we choose here a simple setting. So it's just the Poisson equation with the Dirichlet boundary condition. And in each triangle, we're going to choose a quadrature of this form with positive weights. And we assume that the quadrature is exact on affine functions. So on each triangle, the quadrature rule is exact for linear polynomial functions. And we're going to approximate the integral over the whole domain as the sum of the quadratures on the individual triangles. And this quadrature will be called Q. An example of such a quadrature would be an extension of trapezoidal rule from one dimension to higher dimensions. So it would be given a triangle, you would evaluate the function at the vertices of the triangle, then simply use the linear interpolant between these three vertices to compute this quadrature. We replace the bilinear form by this expression. Of course, instead of the integral, we simply have the quadrature rule, and the right hand side will be the quadrature rule applied to the product f times v. We choose a continuous piecewise affine finite element space. This is exactly the setting for Strang's first lemma. From the lemma, we need this discrete bilinear form AH uniformly coercive, meaning that the coercivity constant should not depend on H. It should have a lower bound independent of H. And we want this difference AH minus A and FH minus F small in certain sense. That is specified by the lemma. Now let's look at the bilinear form first. On one triangle, we can write the difference between the approximate bilinear form and the exact bilinear form in this way. Since we are in a piecewise linear finite element space, the gradient of u and the gradient of v are constants. So this scalar product will be a constant on each triangle tau. That means we can actually pull this constant out, and we simply have quadrature rule applied to the coefficient a minus the exact integral of the coefficient a. The quadrature rule is exact on constants, so obviously integral over tau will be equal to the quadrature rule over tau applied to the constant function 1, and that is explicitly written, can be written in terms of the weights in this way. Then, of course, this integral over tau is just the volume of the element tau, so it shows that the sum of the weights must be equal to the volume of the element tau. If we apply the quadrature rule to an arbitrary function g, it can be written in this way, and we bound g by the infinity norm of g, and by using that the weights are positive, we can derive this bound. So the quadrature rule applied to any function is bounded by the volume of the element times the infinity norm of the function. Since this is constant, now we want to bound that part. We can now introduce any linear function a bar, because q tau applied to a bar is equal to the integral of a bar over tau. So this difference will be equal to the quadrature rule applied to the difference plus the integral of the difference. And at this point we bound this by the volume of the element times the infinity norm of the difference, and the integral can be bounded exactly by the same expression, and so you have twice the volume of tau times the infinity norm of the difference. And the infinity norm of the difference can be bounded by h squared times some norm of a by using Bramble-Hilbert lemma. So basically this difference is now bounded by h squared times the volume of the element tau. Now we sum over tau so that the quadrature applied on elements sum to the quadrature over the volume omega, and these integrals become the integral over omega. So this would be, of course, just AH applied to UV, and this integral is exact bilinear form applied to UV. By substituting this estimate, we get h squared, and remember that we had this nabla u times nabla v in front, so nabla u times nabla v here, and the volume of tau. And now, since nabla u times nabla v is constant, this sum is actually just the integral over omega of this function absolute value of nabla u times nabla v. And by applying the Cauchy-Schwarz, we get this bound. In the end, approximate bilinear form minus the exact bilinear form is bounded by h squared times the h1 semi-norm of u times the h1 semi-norm of v for all functions u and v in the finite element space. Now, just putting v equal to u, you get this estimate, and that actually immediately shows that the discrete bilinear form AH is uniformly coercive in the sense that AHUU is bounded below by alpha. Alpha is the coercivity constant of the exact bilinear form A, then minus some constant times h squared according to this estimate times the h1 semi-norm of u. So this shows that if h is small enough, we get AH coercive, and this constant will have lower bound that is independent of h. In Strang's first lemma, we also need to bound such a supremum, and this supremum can immediately be bounded by h squared times the h1 semi-norm of u. Substituting this bound into Strang's first lemma, we will get this. So on the left hand side, we get exact solution u minus discrete solution uh in the h1 norm. On the right hand side, we have infimum over u in the finite element space, and here we have the constants. We know, for example, alpha h has lower bound independent of h, so this can be really treated as a constant. Here we have the exact solution u star minus some arbitrary finite element function u, and here we have the consistency term coming from the AH, which is this estimate. You have h squared times this h1 semi-norm of u. And then here we should have the consistency term coming from FH, which is here. And now we can substitute for u something reasonable like Strang projection of u star. Then this difference is bounded by h times the h2 norm of u star. And we have stability, so nabla u will be bounded by h1 norm of u star, and we get h squared in front. And the third term is the consistency of AFH, which we will bound next. And just looking at the first two terms, we see that this term coming from the consistency is actually higher order than this main term, so it's not going to harm the convergence rate. Okay, now let's look at this consistency term. Again, we just focus on an individual triangle first. We get quadrature of fv over tau and integral of fv over tau. And just like before, we can now stick in this f bar, which is an arbitrary constant, because arbitrary constant times v is a linear function and q tau is exact on linear functions. And by bounding this, we get twice the volume of tau times the infinity norm of f minus f bar and infinity norm of v. This difference, if we choose f bar, for example, the average of f over the triangle tau, we will get h in front, and we get w1 infinity norm of f. Note that this volume of tau is of order h to the power n. Now we use inverse estimate to bound the infinity norm of v by the h1 norm of v, and we will pick up h to the power 1 minus n over 2. Finally, we sum over all the elements. So here we have the quadrature applied to the product fv, which is just the approximate right hand side fh applied to v, and that's the integral of f against v, which is the exact right hand side f applied to v. From here we get h to the power n plus 1, and we get h to the power 1 minus n over 2 from that, and we get h1 norm of v over tau. Then we will use Cauchy-Schwarz for sums this time. So these two together will give us power 2 plus n over 2, and that's squared, which will give you h to the power n plus 4. Sum over those and raise to the power half. The part that comes from v will give you exactly the h1 norm over omega. The number of triangles is h to the power minus n. So we get h to the power minus n cancelling with h to the power n. We get h to the power 4, and taking square root we get h to the power 2. So again, it shows that the consistency term coming from the right hand side fh is of order h squared. So the overall convergence rate is h. that is determined by the main term in Strang's lemma.